Our next speaker is Curt Dunn with the NDDOT's Grand Forks District, and he'll share his insights on transportive tools for smarter paving. Curt, take it away.
Welcome, and thank you, Aaron. So for the first part of my presentation, I'd like to focus on a project we did in the Grand Forks District this year on I-29. It started from Drayton to the Canadian border. It was about 30 miles on southbound, and the project. The prime contractor was Knife River Materials. The project engineer was Lynette Stain from the Grand Forks District. So it was mainly a 2-inch mill and overlay, but there were some other things on it as well, like concrete pavement repair and PCC grinding and things underneath the interchanges. And we also had some centerline joint repair, which we're going to see in a couple of slides here. So there was several special provisions on this project as well. Longitudinal joint density, which is in pretty much all of them now. But there's also e-ticketing mandatory and paver mounted thermal profile, percent within limits. And then there was a ride specification as well, and intelligent compaction. So this is what the roadway looked like a couple months before we started working on the project. It's pretty obvious we need a mill and overlay, but we also had some real issues with the centerline joint repair, and it's pretty evident there. And so it actually has 4 inches of existing asphalt over the jointed concrete. And but you can see over to the left that you can actually see the joint had deteriorated 4 inches down. You can actually see the concrete there. So out of the 30 miles, there was probably about 10 miles, I believe, that had this issue. So we really couldn't ignore it. We had to fix it. And of course, that's always easier said than done. You want to be able to do it safely so traffic can keep going, and safety for the workers as well. So we had to be a little creative and innovative as we did this. This is really nothing new to the DOT. Actually, Valley City has done a couple of projects with this type of repair. So we got the idea from them, and then there's several other states that have done this as well. So you can see up on the top section there, this is where you see the distressed area there. And so the first thing we did was actually mill off the passing lane. But we went 2 inches more, or 2 feet more past the center line so we could work in there. And then once we did that, then the contractor went in and milled out the rest of the joint area there, which was 2 feet in each side. And then subsequently, we put the overlay on. So we actually had specified density on the patch area as well. So show you a couple pictures of it. This was the milling machine that the contractor used. It was just a smaller machine. And cut a swath about 4 feet there, all the way down to the concrete there on the left. And you can see the joint there after it's been done. Actually, the joint was in pretty decent shape, which was kind of surprising. So once it got swept out, then they tacked it, and then they went ahead and paved it. And I guess visiting other projects that this was on, and talking with other states, I think this was really the first time I've seen it where they actually used a paver and they were able to block off enough so the discrete only, only did for like 4 feet. So I thought that was pretty interesting. It's pretty conventional. They can be done, And then the regular rolling sequence there was a smaller roller in the forefront here. And that was basically the finished product there. So hopefully we get a lot of good out of that. So moving on, percent within limits. This is just a continuation of the North Dakota DOT's effort to get better densities and more uniform pavements out there. And so we had this percent within limits specification. And so with everything, we have inherent, variability out there, especially with highway materials. It basically starts at the source and moves in when we process the aggregates, and then also with the sampling and testing. So we've also, there's inherent variability, but the key is to be able to minimize it and manage it as we go. So percent within limits is an improved way to measure the quality of the pavement. Not only do you get the average density out there, you actually get a standard deviation as well. That's it with it. So they really take that seriously as far as the average and the standard deviation, because you can have your hand in, one hand in hot water and the other one in cold, and you say the average is warm. Well, you never really got any samples in the warm portion. So, that's kind of an extreme, but that's kind of how what they want is a real tight variability out there, I guess, where things are more uniform. So really the PWL specification encourages the use of, encourages uniformity in when they're producing the mix. So this is the final page of the special provision. If some of you might be familiar with this, we've had maybe a dozen of these projects, I think, over the past few years, but the final page is actually the calculations, and they're all statistical calculations, but actually they're really not too bad. So all of this is actually keyed into the paving workbook, but it's kind of nice once in a while to go through it to see, where the dollars and cents are all come about. So I'm just going to go through one real quick here. So this particular day, there was 7 cores taken. So the first thing, you actually do at the end of the day is, run it through an average and 94.9. So take notice of the range there. That's no more than about 1.5%, if that, between the high and the low there. So that's really, I think, pretty good, real good. So once you get that, then you can go ahead and do the standard deviation, which was really also a really good number there. And you take those two values then, and then you can you figure out your upper quality limit and your lower quality limit. And also our lower specification limit for this was 92, and the upper was 97. So the idea here is to really get all your stuff to fall in that area. And so you get those two values, and then you can plot them on your like a standard PWL table. And what you get from that is like your percent within lower specification limit, which was 92, and this percent within the upper one, which is 97. And then you can figure out the last calculation procedure in the upper right there is just figuring out your quality level. And the higher the better for that. So then once you get that number, then you can plug it into the North Dakota DOT pay factor then for PWL. So in this case, that for that particular day was 105 we got, so that's actually 5% incentive, which is the best you can get. So overall, the project had 134 cores on it. There was average density 94.4. There was only 2 cores that were out of under 92, and the lowest one was 90.8. And so actually with this type of the contractors encouraged to push their averages over to the right, say from the 92. If you're too close to the minimum, then the curve there, the variability runs a chance of being out. So it's nice to get your averages, over almost in the middle of the two limits, so you can get everything to come in, pretty well. So. So now we'll kind of switch gears a little bit with some of the technology tools we have out there today. We've been using some of these tools now for a few years on not all projects, but several projects over the state. So first one's intelligent compaction, and that's really just equipment-based technology that helps in the quality control of the asphalt pavement. And so you have GPS equipped rollers that collect data real time on projects, and they collect data like you could. So how many passes have went that it took. So if you have a square foot of pavement out there, by the time it's all done, rolling and stuff and compacted, you have a lot of history on it. Actually, You can tell how many times it went over, you know, with a roller, what type of roller went over it, whether they had vibratory controls or regular just, you know, static. Or it'll even differentiate between what roller went on it. You know, if you have 3, 4 rollers, it can differentiate between that. It tells you what time that it went over it. Also the surface temperature, it records that as it goes over it as well. Speed, amplitude, frequency. So there's a lot of things you can get. We know a lot more about our pavements than we used to, actually, because we have a lot of data on everything. So there's onboard monitoring systems so that the contractor can, or the operator can actually, you know, use it as a guide to see how many passes they do or what the temperature is as they're going. We also have paver monothermal profile out there as well, and that's more of that's a paver-based technology. It has infrared cameras, and it is as the paver goes through, it scans full width all day long, and so it gives you a surface temperature profile, as well as, you know, potential for segregation, material segregation, thermal segregation, things of that nature. And it also has onboard monitoring systems as well that can be on the paver so the operators can watch it, and that's basically real time as well. And also density profile system. That wasn't a special provision, but North Dakota DOT has been experimenting with this technology for several years now, and actively comes out and has collected a lot of data on quite a few projects over the course of the few years here. And so it's basically ground penetrating radar that's full coverage, provides it's non-destructive. And so it's really a testing alternative to evaluate compaction, say, versus your cores and your nuclear density machines and things like that. They're basically spot tests, but this is actually full coverage, so that's the advantage of it. So more on that a little bit. So all these 3 technologies that we just talked about, they can actually be analyzed and mapped and in a software called Veda, and Veda's been around for maybe about 10 years, and it keeps being developed as it goes, and so it's really just a way to view all this geospatial data. And so a little bit more on that. So I've got a few slides I wanted to talk about with some of these, where we actually put the technologies all together in like one slide to kind of see some things. So that this is still on I-29 here, where there was one core that was a little bit lower. In fact, it was the lowest one on the job, and so it lagged behind the others maybe 3-4%. And so you can go in there and kind of see, well, do some forensics on it, for instance, and see what really happened. So the core. So over to the left there, you have the paver monothermal profile, which comes from the paver technology, and over to the right, in the middle, and to the right is actually the roller-based technology from the compactors. And so the one over to the left, you can see that the core, and you can plot this in Veda as you want, and you can see it actually fell in some really nice temperatures behind the paver. But it didn't, and even over in the middle, you can see there's quite a few passes that went over it. In fact, probably more than 8. I didn't have the legend up there, maybe high enough, but but then if you filter it out a little bit more, where you have just passes, say, over 180 degrees, and 180 degrees is like an arbitrary value that has been agreed upon over the years, that if you try to compact anything under that, you're really not going to get any more results. It's cooled enough where it's not going to really help you any. So you can filter it out to actually show those temperatures over 180. And you can see that it really only got about 1 or 2 passes. So why would that be? And it could possibly be that maybe it's because of that paver stop there. There's a 22-minute paver stop. So, you know, maybe 3-4 minutes, the rolling sequence doesn't really get out of, you know, out of sequence, but when it gets to be that long, then things start to stop, and, you know, everything stops. And starting up again, then maybe it's not the same rhythm as it was. And, you know, and that might have had something to do with it. You know, you can even notice right at the paver stop over to the right, there is no passes. There are hot passes, so, you know. Now, here's a good core, 95.3. So, you know, it fell in some really nice temperatures in the thermal scan. And over there to the right, I just have it filtered out to the passes over 180 degrees. And you can see it fell in some really nice passes there as well. So over to the left there, you can actually go into this Veda program. And, you know, you can do an analysis. And so every one of those blue dots there that you see, that's actually when a roller hit it of some sort. It tells you, you know, how many minutes since it started rolling, and you can see, I think we count them up there as maybe 11 or 12 passes. So there was actually that many on that area. So, you know, that might be a good, you know, reason why that core turned out so good. So usually there's a story behind most of it, most of the time. So now I took that same data that was just in this previous slide and put it into the PaveCool program. Probably many of you have used that. It's older technology. It's probably been around since some of this new technology's come along, but it actually, you know, plotted it pretty good as well as far as time for compaction after the paver goes over it. So within a minute or so. Okay, this is the first I'm going to show of the density profile system, which is over to the right. So over to the left, you have the paver, the profile, or the thermal profile, and we have a little paver stop there in 26 minutes. In the middle is the hot passes, or the over 180. And once again, you see there's not very many in there. Well, it really showed up. It's very sensitive to the density profile system to that. So that's how sensitive it is. Once again, the same thing, basically same slide here, or same situation. You could even tell where they're like in the middle, you have a couple passes there that were kind of left to the left there on the top. It actually reflects that in the density profile system. So this particular photo here is just a close-up of a paver stop in Veda, if you've ever seen it. And really what's happening here is you've got the pavers moving left to right, and it stops for some reason. And so it's sitting there for a amount of time. And you see it at the bottom, at the lower there's the thermal scan. When it comes off the camera, it comes off at an angle. So it actually, by the time it hits the ground, it's maybe 8 to 12 feet back of the screed. And so once the paver starts going again, it actually scans that area that's probably cooled. And so that's why you see that darker blue area there. And the area there just to the left of the blue, which is a little brighter looking, that's actually the heated screed that's been going, you know, since it stopped. Yeah. So, okay, I got to keep going here. So here's some more passes, just some more things here with the density profile system. You got more passes, less passes. The concentration of the greater densities are in the density profile system there. Same thing with this as well. More passes, less passes, more density, where you have more passes. And this particular screen here actually differentiated between, and you can do this in Veda, you can differentiate between the different temperature or the different densities. So in this case, we'll just take the right there. The lesser densities from 94 down were actually situated in the areas where there was less passes. You can do some analysis in Veda. We actually did with the dielectric, or with the profile system there, the density profile system. You can plot all that, and actually we had the densities were actually right up, you know, right average with the cores. And same thing with this. I think, you know, we always compare the density profile system to the cores, but I think we should be comparing the cores to the density profile system myself. I think this is the most accurate. Thermal segregation, if you look at it Veda enough, you'll see some, you know, places where you see a lot of segregation. You know, this is pretty cyclic. You know, I have a question mark there because I'm not really sure what's actually, maybe some of you do, but benefits of uniform temperatures. This is just taking a thermal camera with someone in the back of a paver, and you can see there's some really nice temperatures there across. If you can get it to that point, that's really good. Longitudinal joints, we started looking at these about 10 years ago, and at that time we took some information cores when we weren't really doing anything. We couldn't core within a foot of the joint at that time. But you can see, you know, that one project was actually 83.3 average, if you can imagine something like that. And now you can pick just about any project, and you're getting, you know, 92.8. That was just a typical day of a random project. So I think a lot of this are looking at this now. Actually got, you know, some innovation going with the notch wedge joint, things of that nature. E-ticketing, another technology that's come around now. Without any doubt, I think it saves lives, money and time. I think there's reduces or it improves the data collection and reduces the you know, information loss. So last year we had 1.2 million tons at, say, an average of 25 tons per truck. You got maybe 48,000 tickets we would have had to deal with, you know. Either loot, maybe some of them get lost. When you're transferring data over to them, you might lose, you know, some of that. So I think this is a win-win. I think it really helps the contractor to make their flow rates and cycle times more efficient by using this technology as well. So there's a new standard out there. Just wanted to let you know. Was just approved by AASHTO. It's called Material Delivery Management System. And so when they were developing this, and actually MnDOT was the steward, and so when the user groups were looking at all this, they decided that they wanted maybe just a little bit more, so maybe some extra data collected once it leaves the source, or maybe past the e-ticket, and maybe look at some stuff like split loads and where all the loads are going, multiple bid items, reconciling quantities. They also added some fields so that they could support groups like labor compliance and civil rights activities and things like that. So it's kind of a grocery store of things out there. We don't have, you know, a big part of it is e-ticketing, but there's other things too later on down the line. So the future of Veda, Veda right now is a desktop platform. It's mainly for post-construction analysis. It wasn't really intended to be real-time. It kind of left that up to the proprietary softwares. But now is being moved from that to a web-based platform. I think there's going to be piloting some in MnDOT this year. And so it's going to have a lot of new things. In fact, you can even plot all the e-ticketing stuff on it as well, and then compare that with all your other technologies. And so, you know, there's a lot of good benefits I think that's going to come from this, and you know, be able to run it on your laptop in the field or a mobile phone, and map the number of, you know, keep track of your trucks. I think one of the biggest things I like about it is it's going to be able to work with the near real-time things that are going on in the field, so you can make some quick decisions with what you come up with. And I think that's really going to help, because that's what all this is all about. That's why all this technology was developed, to help in the quality control. And so with that, so anyway, what our big goal in all of this and using all this is to get better performing pavements and longer lasting pavements, and that's the big goal. And I think that all these technologies, if they're used, can be effective in helping with that. So with that, that's all I've got. So
let's give Curt a round of applause.
Oh, thank you. Thank you. Thank you.